complex topics, eutectic transformation. The practical relevance of the transformation, real metals must solidify authentically or periodically, depending the general understanding of state diagrams. Preparation for static complex real state diagrams. So we will start with Coulomb curves. As we have seen before, here we have a liquid phase, liquid plus cadmium, liquid plus bismuth, cadmium. And if we transform it to the phase diagram, which we have seen in the previous chapter, we get here liquid phase, liquid plus cadmium crystal, liquid plus bismuth crystal, and here we have bismuth crystal and cadmium crystal, and they are divided by a eutectical line. Complete solubility in the liquid state and complete insolubility in the solid state. Structurally, we can this graph. So here's concentration and temperature. So there is a phases alpha crystals and beta crystals. Here's a liquid phase. Here's phase plus alpha crystal and liquid phase plus beta crystal. So when we have high temperatures, the alloy is fully in the liquid state, so L. When we start cooling this liquid, it starts to harden, making one of solid phases. So it's a liquid plus alpha, liquid plus beta. Here we have a eutectic point. It's a point where a liquid transforms momentarily in the two solid phases. So alpha plus beta without any transition distance. And this happens with eutectic temperature and eutectic concentration. So complete solubility in the liquid state and limited solubility in the solid state. So before this eutectic point, we have hyper-eutectic, primarily alpha crystals, and after this line point, we have hyper-eutectic, so primarily beta crystals. So at points 1, 2, 3, and 5, we have a liquid phase here. So concentration of liquid, C liquid. So at first point we have 40% concentration B. As points 2, 5, we have 60% concentration of component B, and at third point we have 80%. And the ratio liquid divided by M total is 100%. In the point 4, so liquid plus alpha crystals, we have liquid and alpha phases. So solid. And C liquid is 48%. Component B. And M liquid divided by M total is 79%. And alpha crystals, the concentration of alpha crystals is 10% component B. And the mass of alpha crystal divided by M total is 21%. In point 6, we have liquid and solid beta crystals. So say liquid is 72% B component. Here. And M liquid divided by M total is 60%. So in beta crystals, the concentration of beta crystals is 84%, or 94% component B. Here. And beta crystals divided by M total is 6%. And then 0.7. 0.7, where is alpha plus tectoid and beta segregation. We have alpha, so it's 7% approximately here. It's of component B. Cu tectoid, so it's 60% component B. And segregation of beta crystals concentration approximately here 96% component B. And then we can divide, then we can find M component divided by total. So we have here eutectoid, alpha, solid and beta segregations. It's 0.8 here. Here we have 60% of component B. So eutectoid concentration. And the mass of eutectoid divided by total mass 100% and 10.9. So we have here solid beta, alpha segregation, and eutectoid. So concentration of beta is 96%, eutectoid 60% of component B, and alpha segregation. So it's here 7% of component B approximately. And in this case, alpha plus beta segregation, we have alpha solid and beta segregation, and here we have beta crystals and alpha segregation. So rows of a tactic solidification front. So here 7 M mass of alpha divided by M total. 6%. Eutectoid divided by M 60%. And M segregation, beta segregation divided by M total 4%. And it's similar for 0.9 for beta crystals and alpha segregation. And we can transform it to another graph. We calculate here points 1 and 2. So we can construct auxiliary lines. And on the x we have component b in percent, concentration, and phase fractions in percent. 0 to 100. So we can draw dashed lines from these values using auxiliary lines. So alpha, beta segregation, alpha segregation, and diptychoid, both solid phase alpha and beta. So mass of unit divided by m total here, m beta divided by m, this range, and m alpha segregation divided by m. And we will also have a set of beta, alpha, and so beta, and so on. So these particles are moving alpha A component is moving to alpha, B component moving to beta. So tectic is from Greek good melting. But tectic is a term for a system of two and more components that mix completely in the liquid state but are immiscible in the solid state. Mix liquid state and immiscible solid state. Now, compared to the melting point, the starting components largely decrease in melting point occurs in eutectic. In eutectic alloys, the solidose and liquidose temperature coincide. The transition from solid to liquidose occurs without the solidification interval. This transition is called eutectic point. Hypoeutectic alloys, so about to the left of the eutectic position, composition precipitate primarily alpha crystals and eutectic during solidification, and hypereutectic alloys close to the right of eutectic composition precipitate beta primarily crystals and eutectic. Neurotectic alloys are materials close to the eutectic composition. So here we have eutectic line, horizontal connection line between the three phases involved in the eutectic reaction. And eutectic reaction, the composition of a melt at fixed temperature and composition into two solid solution. So from eutectic, we get alpha. And here we have exercise. So the answer you can see the file regarding the question 2 and 3. Why is the eutectic alloy particularly suitable as a casting alloy? So low melting temperature is economical melting, low viscosity just above melting temperature, high melt filling capacity, modification without segregation, and uniform properties. What is the purpose of microstructure diagram? Planning a heat treatment determination of tendency to segregation, prediction of this furnace dimensioning, temperature range. Have here table for concentration temperature for this graph. And here we can change parameters. And now we will go on with our first lecture. So iron carbon phase diagram. Iron carbon phase diagram. Ferrous metals are the most technically important materials. Understanding of the different modification of steel and iron depending of which from metal systems. So equilibrium state and solid temperature changes. Here we see a regular phase diagram. Iron, you've seen before. And allotropic transformation or polymorphism is a transition of material from one crystal structure to another at given temperature. So iron changed from a body centered cubic BCC to 5 centimeter cubic structure when exceeding 110 degrees Celsius, and increase of packaging density, so it's higher density and volume reduction. So from alpha base, so base cylinder cubic structure to gamma cylinder cubic at temperature at least 910 degrees Celsius. Stable and metastable iron carbon phase diagrams. So here, variety from the carbon metastable systems, carbon which is no longer soluble in crystal lattice, say alpha, beta, and alpha, gamma, and delta phase is present in the form of cementite, ferrum silica. This metastable solidification occurs at rapid cooling and in the presence of carbide-forming elements, for instance, magnesium, manganese. Cementite decomposes into iron and graphite long annealing times. High temperature. Carbon stable system. Carbon which is no longer soluble as a crystal lattice is presented in the form of carbon graphite as a stable system formed during cell cooling and in the presence of graphite decomposing elements, for instance, lithium. And the metastable system is technically more important one since steels and some iron castings solidify accordingly. So iron carbon phase diagram, ICPD. So metastable cementite system. We have here endpoints. Delta phase, liquid plus delta phase, liquid and primary cementite, liquid plus austenite. Here at start we have austenite or gamma. Is austenite and secondary cementite. Austenite plus laterite one, secondary cementite, primary cementite, laterite one, and secondary cementite. Here we have the cementite. A bit of info, phase, then we have ferrite and perlite, perlite and secondary cementite, perlite, laterite 2 and secondary cementite, primary and secondary cementite, and laterite. Here we have divided in behavioral range, so hypertectoid, hypertectoid, hypoeutectic and hypoeutectic. Okay, it's a white cast iron. It's steel. So and so you can look into different concentration ranges and the phase area. For instance, here is ABCD, BBCD. So it's just liquid. It's eutectic and tectoid. This temperature. And we have a gamma phase. It's austenite. So when the liquidus line BC is reached, low carbon austenite crystals precipitate from the melt. And BC. Have eutectic reaction at EC. So eutectic reaction at this temperature, residual melt concentration 4.3%, to austenite plus latabarite 1. And primarily precipitated austenite crystals. So the phase area below E and C, it's austenite plus latabarite 1, cementite. It's eutectic, primarily precipitated austenite crystals and austenite from laterite 1. Aggregation of cementite with falling temperature. We have SK line, the remaining austenite and austenite latabarite 1 crystals. We get perlite, cementite from latabarite 1 is labarite 2. Phase area next to DCF. When the liquidus line CD is reached, acicular from C carbon lemon precipitate from melt, so it's primary cementite. We have eutectic reaction CF. So this is the melts at this concentration, austenite plus latabarite 1 embedded at the acicular rapidly cementite. This area below CF. Percent plus latabarite 1 technique primarily precipitated austenite crystals, segregation of secondary cementite temperature agglomeration to primarily room 3 carbon, and it's not visible in hyperstructure. Here we have area below SK, austenite crystals Molecular 1 to paralyze integrated composition of the cementite from molecular 1 to molecular 2 and primarily cementite structure molecular 8. Here we have GP, which is alpha crystals with critic microstructure, CC. What is it? And face area below vacuum. You decrease in carbon solubility of the variety with dropping temperature. There's DRA cementized chain boundaries. So here we have austenite area GS E I and M. Just it says this GPS area is austenite crystals and alpha aggregation. Alpha start transformation. Here, green boundaries, change the structure, facing for the center qubit. Here we have area base area PS. Hyperductoid still. From fluoride precipitates. Have detected the composition of austenite area below and S, which is parallite. Formation of detected phase parallite. Unparallite, cementite compound. SKE. Yeah. Primarily cementite precipitation at A1, which less temperature, so temperature less more than A1, let's say A cementite. Here we have variable SK, detected austenite, composition at 723 degrees, shell depth cementite at green voltage. Here we have overview of phase of pure iron. So transformation at equilibrium, transformation at cooling, transformation at heating. The different phases of pure iron are called allotropic modification. Is number 6. So temperature transformation diagrams, heat treatment of steel, quenching and tempering. So temperature transformation diagrams, its time-dependent process are characteristic for industrial heat treatment. Many material properties of steel are explained by your TTA diagrams. So it's TTA time temperature austenitization. Heat treatment of steel still acquires its industrial significance through the targeted adjustment of the stereotyped microstructure. So rapid temperature changes. equilibrium diagrams. This is thermodynamic equilibrium. Night, slow cooling, heating respectively. Technical process, however, the place in a short period of time. In time temperature transformation, consideration of incomplete diffusion processes, consideration of time as a parameter, time temperature transformation diagrams take these effects into account. So it's high technical requirements. So we combined just two planes, one with continuous cooling transformation phase diagram, with temperature time, and equilibrium phase diagram of unalloyed steel. Here we have temperature and carbon content. So in continuous cooling transformation, there are phases like ferrite, pearlite, austenite, martensite, bainite. In equilibrium phase diagram of unalloyed steel, there is phases austenite, ferrite plus austenite, ferrite plus pearlite, pearlite plus carbide, ferrite, austenite and carbide, austenite and carbide. So time-dependent transformation, continuous cooling transformation phase diagram. So time temperature transformation diagrams are an important tool for technical execution of heat treatment of steel. Structural constituents formed during cooling can be defined for continuous cooling and isothermal transformation. Here we have continuous cooling. Hyperheated steel. So when time is around 10 seconds, the when time is 150 seconds, and temperature 710 degrees, formation of ferrite and austenite grain boundaries. So austenite and ferrite grain boundaries here. Point. Here start of paralytic transformation after 50% ferrite is formed. Here completion of paralytic transformation. Final macrostructure, half ferrite, ferrite, separation. In this graph part, here we have AC, A1 lines, T to 0 seconds start. So here we have start of ferrite transformation, start of parallel transformation, completion of transformation. Here we have a final macrostructure, a quarter of ferrite, a 3/4 of pearlite, case of elimination. ODCT is also called isothermal transmission diagram. Shows how the macrostructure of steel changes depending on temperature and time. once again, with the y-axis we have temperature, x time, logarithmic scale, and be from milliseconds to hours. And we have transformation curves. So S-shaped curves indicate the start and the end of transformation, different temperatures. At high temperatures between 600 and 700 degrees, austenite transforms into perlite. At intermediate temperatures, from 600 degrees, we have binary forms. And if cooled rapidly, below the Martensite start temperature, so there forms Martensite, which is hard and brittle. So speaking in general, for slow cooling, we have perlite, which is soft and elastic or ductile. In moderate cooling, we have bainite, so it's strong as a perlite, less brittle than martensite. And in rapid cooling or quenching, we have martensite, which is very hard but brittle. So quenching and tempering, while metals harden, general components are useful as long as no impermissible plastic deformation occurs. This essentially corresponds with the plastic region, the stress strain diagram. This range is small for soft materials. They are generally poorly suited as construction materials. The range is large for hard materials. They're usually well suited as construction. This gain of higher variable force stresses can be used in technical design. So here we have stress and strain as axis. So for hard materials we have high strength, and soft we have limited strength. Quenching and tempering of steel. This consists of quenching or hardening, tempering or reheating the temperature up to 650 degrees. So hardening and reheating. With the hardening, change of dimension changes. Here effects of tempering the dimension capacity of hardened or pieces, thus service properties are improved by tempering. Residual stress are reduced and reduction of risk of cracking. So here's also the diagram for process quenching and tempering temperature and time. So start, we have austenite sheet temperature. We start with rapid heating. Then we have austenization around 850 degrees. Then we have quenching, martensitic transformation, rapid cooling. Then we have bit of increase, so plateau, tempering at 500 degrees Celsius around, formation of glass hardness. Then we have this. So here we have a combination of face centers, cubic lattice, and body center tetragonal lattice. So position of iron atoms here, austenite, possible position of carbon atoms, lattice. So the sand cell implementation mechanism. Strength increase due to mortise formation. Benefits of dislocation motion in side crystal. First, advantage trigonometric distortion due to supersaturated solution with carbons that leads to strong stress fields in crystal lattice. Supersaturated carbon has a solid solution strengthening effects, increasing of inner tensions within the crystal lattice. As a result of the transformation process, lattice defects, especially dislocation, occurs to work during mortisite transformation. Internal interfaces are formed, so obstacles for dislocation. Precipitation hardening of aluminum. The majority of aluminum application require a strong and hard material. As mentioned, it's a key technology for optimizing properties in aluminum. What's called edge hardening? First, always edge hardening or precipitation hardening is the most important measure for achieving high strength. Aluminum alloys in particular hardly have significance as construction materials without the possibility of edge hardening. The conditions precipitation hardening that have better scalability at higher temperature, so homogeneous solid solution than a low temperature. Precipitation of a second phase during slow cooling from the analog temperature. Quenchability of the alloy. Retention to the homogeneous solid solution during rapid cooling from analog temperature. So on this we have temperature and here we have second phase during slow cooling, segregation and homogeneous solid solution of reduce phase. Sequence of isolation hardening. So we have here salt. Equal distribution of aging emission, annuals process facilitates by controls stimulation process suppressed during cooling. So we have solution. Freeze. Then we have quenching, rapid temperature. And we have other aging. So we have an artificial aging. This big place and it's pitching. For instance, from a routine sheet certain areas. This platelets or needle-shaped areas are called linear Preston zone 1, GP zone 1. GP1 zones are monoatomic layers less than 10 nanometers that are coherent to the matrix lattice. The increase in strength zone 1, which generate the instant force levels of dislocation. Artificial aging by the temperature of treatment. During artificial aging, So from 80 to 100 Celsius, the shape will represent to zone 2, several atomic or thick unformed clusters. They are also coherent but larger than GP1 zones. Above 150%, the metastable and partial coherent database is formed. When GP2 and databases are present, the hardest maximum is reached. Database represent one space of hardening, so loss of strength is tolerance. So here we have hardness maximum for level GP2. Base at the base curve. Here we have hardness, the aging time base. We have temperature precipitation diagrams following you. So many aluminum cores show highest when delta prime that simultaneously occur. Above 200 degrees. So above 200 degrees, GP1 zones are unstable, possible formed zones dissolve again. After 10 hours of aging at 150 degrees Celsius, the dominant precipitate is GP2, or also called delta prime. Start of precipitation at Greener Preston zone 1 at 150 after approximation 4 seconds, shortest time of ice rate. Then we have start of precipitation of GP1 at 25 degrees Celsius after around 6 minutes. And here we have a scheme of data phase equals incoherent phase body centered tetragonal. So M2, delta prime partially coherent phase tetragonal, delta 2, GP2 zone, coherent phase, 2 layers of cuprum separated by 3 layers of aluminum here, and GP1 is in plates of cuprum atoms on hungry plates in the pressure aging logarithmic diamond house. Is delta phase. Prime. That's 2 prime, so GP2 zone 0 precipitation hardening, H hardening, particle hardening. Precipitation can hinder dislocation movement, very effectively strengthening effect. Resting side, the precipitation are small, from 50 to 100 nanometers and annual disposed. There are two interaction mechanisms, sharing mechanism and circumvention mechanism. So shear mechanism, freedom effect, we have dislocation, force down, precipitation, external shear force causes dislocation to move in their slip planes. The dislocation moves through the precipitation. The shear mechanism, the precipitation is sheared or cut by the dislocation. The precipitation plays steps. In the process, the two halves of the particles are irreversibly shifted against each other. So I shown here. Mechanism. So we have here precipitation and precipitation. Here goes down. So due to external shear force, magnetic dislocation is stopped. Particles lying in a slip plane. Dislocation built up to different phases. The further movement of dislocation requires a high shear stress, reasoning, and further movement of dislocation. Then we have oppositely oriented dislocation segments which attract each other, plus minus. Then we have replacement annihilation. The dislocation ring remains around the precipitation. So here's precipitation and dislocation ring. The free sliding dislocation can influence the particle size. So bypass or mechanism. So delta omega is proportional to square root of the A, and the B is particle diameter, small particle diameter, increasing shear stress strengthening. Then we have shear mechanism, delta omega proportional to 1 divided by particle diameter. Large particle shear is independent, provided, so there is strengthening. So here we have sequential shear mechanism. So particle hardness rises. Here we have shear and circumvention here. So summary of precipitation hardening. Precipitation hardening is a heat treatment to increase the hardness and strength of noise. The process is also referred to as SH hardening. It's based on the precipitation of metastable phases in finite dispersed form, so that they represent an effective obstacle dislocation. Precipitation hardening is way to increase the strength of volume. Always since they don't exhibit polymorphic transformation, thus cannot be hardened outside formation. Diffusion-dependent process occurs to martensitic hardening in the supersaturated solid solution, depending dislocation movement of precipitation. What must be the solubility of two metals in the solid state to allow precipitation hardening? The matrix metal must have a limited solubility for the aluminum component, which decreases with temperature. What is the cause of precipitation hardening? Presence of metastable supersaturated solid solution of the solution, heat treatment, and quenching. Precipitates are formed during aging. What is meant by aging? Particles coursing due to too long aging. Large particle spacing
and incoherent attachment to the matrix lattice, so it's less effective obstacle to its location movement, so the resistance decrease. What are the three processes involved in precipitation hardening? So it's a formation of precipitation, loss of precipitation, and coarsening of precipitation. What is the difference between natural and artificial etching? Natural etching, so diffusion process take place at ambient temperatures hours to days. Artificial etching acceleration diffusion process at 80 to 200 degrees Celsius are hardened a shorter time. Which listen here, and the next lesson will take last four presentations, and we will discuss quickly some excellent tasks.